Before the universe existed, there was nothing. And this nothing wasn't empty. Physicists describe the state before everything as a sea boiling with hidden energy. Quantum fluctuations continuously created and destroyed particles in fractions of a trillionth of a second. From this invisible chaos, galaxies, stars, planets could emerge, including us. But here's the unsettling question. If the before itself didn't exist, how do we even know what it was like? Try to imagine erasing everything. Absolutely everything. Walls, air, the ground beneath your feet, stars, the space those stars would occupy. Time itself, where anything could happen. No up, no down. No before or after. Not a single point to hold on to. Darkness. But even that word falls short, because darkness implies space without light. Here, there was no space at all. This state, that's what physics offers instead of the usual idea of emptiness. Wait, if there's nothing there, not a meter, not a second, not a single coordinate, how can anything emerge from that? You'd think absolute zero would only produce more absolute zero. But here's where things get strange. What we usually call nothing isn't really empty at all. In quantum physics, it's a physical entity. It has its own properties, its own energy, and its own behavior. In modern theoretical physics, nothing isn't a hole or an empty void. It's a quantum vacuum, a medium filled with hidden energy and brimming with possibilities. Think of it not as an empty room stripped of furniture, but as a boiling cauldron where pairs of virtual particles flash into existence and vanish every fraction of a second. They appear out of thin air, live for an incredibly brief moment, then annihilate each other. Yet they are real. So real, in fact, that their effects can be measured in a lab. In 1948, Dutch physicist Hendrik Casimir predicted this phenomenon. Experimental confirmation came nearly 50 years later in 1997. Place two metal plates less than a micrometer apart inside a vacuum, and they attract each other. Virtual particles, those that are supposed to not exist, push the plates together. The void itself exerts pressure, quite literally. Now, consider the scale. The energy packed into just 1 cubic centimeter of quantum vacuum, by some estimates, surpasses the energy contained in all the observable matter in the universe. 1 cubic centimeter. That's about the volume of a sugar cube. And within it, calculations suggest, there could be more energy than in every star we see scattered across the night sky. The number sounds unbelievable. Physicists still debate how to interpret this result correctly. The gap between theory and observation spans an astonishing 120 orders of magnitude. This isn't a small percentage error. It's a difference so vast, we don't even have everyday terms to grasp it. But one thing we know for sure, the state before the Big Bang was not space as we understand it. It had no up or down, no direction to move in, and perhaps hardest to grasp, there was no time itself. Not that time passed with nothing happening. Time simply didn't exist. There was nothing to pass. No before, no after. Seconds, minutes, epochs, all products of the Big Bang, not its background. It creates a strange picture. We tend to think of nothing as the simplest thing there is. Empty, absent, boring. But physics tells a very different story. Nothing might be the most complex state of all. A state bursting with potential, ready at any moment to give birth to an entire universe. And one day, if the word day even applies in a timeless state, it did just that. But the idea that the universe had a beginning? That's far from obvious. Just 100 years ago, the greatest minds on Earth believed the opposite, that space was eternal, unchanging, and had never started from anything. It took one determined astronomer and a single telescope perched on a mountain in California to flip that belief on its head. Albert Einstein could have discovered the universe's expansion a full decade before Edwin Hubble. His own equations, published in 1915, clearly showed one thing. Space cannot stay still. It must either expand or contract. But Einstein didn't want that. He was so convinced the cosmos was eternal and unchanging that he added a special term to his equations, the cosmological constant, designed solely to keep the universe steady, a prop holding up eternity. Here's the interesting part. Einstein wasn't alone in this view. For a long time, scientists believed the universe was static and eternal. This wasn't just a scientific consensus, it was almost a philosophical truth. The idea traced back to Isaac Newton, who in the late 17th century described an infinite space evenly filled with stars. Then, in 1826, Heinrich Olbers posed a paradox. If the universe is infinite and eternal, the night sky should shine brighter than the sun. No one found an answer, but they didn't abandon the model. Later, in 1917, Einstein wrapped this belief in the mathematics of general relativity, lending the old idea the weight of the newest physics. Each layer only reinforced the illusion. The universe was, is, and always will be, forever. In 1929, at the Mount Wilson Observatory on the San Gabriel Mountains in California, 1,442 meters above sea level, the Hooker 100-inch telescope stood tall. At that time, it was the largest telescope in the world. Edwin Hubble wasn't your typical armchair theorist. Before diving into astronomy, he earned a law degree at Oxford, boxed well enough to be offered a shot at the professional ring, and served in the Army during World War I. When he returned to telescopes, his hands were tougher than most of his peers. That toughness mattered. Observing at Mount Wilson meant long hours in freezing wind, with temperatures dipping below zero. But without one man, Hubble might have stayed just a good observer. Milton Humason was a former mule driver delivering building materials up the mountain while the observatory was still under construction. He stayed on with the telescope, began assisting the astronomers, learned how to prepare photographic plates, and over time became the best observing assistant in the entire observatory. He was the one capturing spectra from distant galaxies. The work demanded insane precision, with exposures lasting 20, 30, sometimes even 45 hours straight, night after night, winter after winter. Hubble interpreted the data. Humason gathered it. Without his plates, there would have been nothing to interpret. The data revealed something remarkable. Light from distant galaxies consistently shifted toward the red end of the spectrum, what we call redshift. This meant one thing: galaxies are moving away from us, and the farther a galaxy is, the faster it speeds away. Imagine standing inside a loaf of raisin bread as it bakes. The dough expands, pushing each raisin farther from every other. Not because the raisins move, but because the dough itself grows. Now replace the dough with space itself, and the raisins with entire galaxies. They drift apart, in every direction at once. The universe was expanding. Let's pause here, because this observation leads to something even stranger. If everything is flying apart, that means it all used to be closer together. Rewind the clock. Galaxies draw near, space contracts, matter compresses. The farther back you go, the hotter, denser, and tighter it becomes. If you imagine following this process all the way, all the matter in the universe converges into a single point, a cosmological singularity. Not a small sphere, not a compact region, a point with infinite density and infinite temperature, where space and time cease to exist as separate concepts. One observation, a reddish glow on a glass photographic plate, turned the world's understanding upside down. The cosmos wasn't eternal, it had a beginning. This wasn't a philosophical debate, a religious claim, or a speculative guess. It came from direct evidence, backed by hundreds of spectrographs captured from a mountain in California. Later, Einstein called his cosmological constant the biggest mistake of his life. The universe didn't need crutches, it moved on its own. There's one crucial detail that's easy to overlook. The very expansion of the universe, the key fact that allowed us to detect its birth, works against future generations. Galaxies are speeding away faster and faster. In tens of billions of years, the most distant galaxies will cross the horizon of observability and vanish forever. the cosmic microwave background will fade until it becomes completely undetectable. No matter how brilliant future astronomers might be, their telescopes will reveal only their own galaxy, nothing beyond. No signs of expansion, no clues to a beginning. They will find themselves trapped in the illusion of a static, eternal cosmos, the very illusion we have just escaped. So the universe had a start, a single point of singularity. But what exactly is that? A state where all known laws of physics break down. And how could an entire cosmos unfold from it in a fraction of a second? Here's the catch. A cosmological singularity isn't just an incredibly tiny point. It's a state where density and temperature shoot toward infinity. The equations of general relativity, the only language we have to describe gravity and space-time, stop making sense. You plug values into the formulas and end up dividing by zero. Physics doesn't say, "This is what happened here." Physics says, "I don't work here." And this isn't a temporary glitch or a matter of needing a more powerful computer. It's a fundamental limit of the tool itself. And then it gets even stranger. As far as we understand, time itself began at the moment of the Big Bang, not in the sense that clocks suddenly started ticking, but before that instant, there was no concept of before. Asking what happened prior to the singularity is like asking what's north of the North Pole. Grammatically, the question makes sense. Physically, it's meaningless. The cause and effect chain, which shapes all our intuition, breaks down exactly at that point. And this is where the real mystery begins. You might expect the answer to come from quantum gravity, the theory that aims to unite quantum mechanics with general relativity. For decades, physicists have tackled this challenge. String theory, loop quantum gravity, Roger Penrose's Twister program. None have produced testable predictions about what exactly happened in those first moments. Quantum gravity remains unfinished. Yet the answer, partial and far from final, arrived from a very different direction. Not from attempts to patch up the singularity, but from efforts to explain something much more down to earth. Why the universe around us looks suspiciously smooth. In 1980, a young physicist at the Massachusetts Institute of Technology named Alan Guth wrestled with a very specific problem. The cosmic microwave background, the thermal imprint of the early universe, showed the exact same temperature in every direction, matching down to 100,000th of a degree. Yet, regions at opposite edges of the observable universe could never have exchanged light or heat. They were simply too far apart. So how could they have the same temperature? Imagine walking into two houses on opposite sides of the planet and finding both thermostats set to exactly 21.6 degrees. Just a coincidence? Guth proposed an answer that would upend cosmology. His inflation theory suggests that in the first fractions of a second, around 10 to the minus 35th of a second, after the universe's birth, it went through a phase of exponential expansion. Not slow, not linear, exponential. In other words, it doubled in size over and over again, dozens of times, in a span so brief it's beyond our ability to measure or even truly grasp. Here's the fascinating part, where reason itself starts to stumble. In a fraction of a moment, a region smaller than a single proton by billions of times expanded to a size we can actually grasp. A proton measures about a femtometer across. That's 10 to the negative 15th power of a meter. A human hair is 100 trillion times thicker. And yet, the space from which our entire observable universe emerged was billions of times smaller than that tiny proton. Then, in less time than it takes for an atomic nucleus to beat twice, that point ballooned into something you could hold in your hand. A ball about 8.5 inches wide. You could set it on a table, look right at it, and realize that within this small volume, the entire cosmic blueprint was already set in motion. Here, a question naturally comes up. Wait, how is that even possible? Nothing can move faster than light. That's a fundamental law of relativity. Yet the expansion clearly exceeded the speed of light, by a wide margin. But here's the twist. Relativity forbids objects from moving through space faster than light. What expanded was space itself. The particles didn't race away from each other. Instead, the fabric of reality stretched between them. Imagine a pattern drawn on the surface of a balloon. The dots don't crawl across the rubber, but the distance between them grows because the balloon is inflating. Einstein's theory remains intact. It just wasn't meant to describe this. The consequences of this stretching triggered a cascade that shaped everything that followed. Space smoothed out. Any tiny curve that might have existed in a microscopic seed stretched so thin it vanished, like a wrinkle on a deflated balloon disappearing when you blow it up to the size of a car. The universe became geometrically flat. Temperatures evened out because every point we see today on opposite edges of the sky were once neighbors pressed tightly together in this sub-proton-sized patch. They exchanged heat before cosmic inflation blew them apart across billions of light years. Yet, and this is perhaps the most astonishing part, the tiniest quantum fluctuations, random energy jitters in that microscopic spot, didn't disappear. They stretched along with space itself. Those subatomic tremors expanded into structures on a cosmic scale. These stretched-out irregularities became the seeds around which matter would, hundreds of millions of years later, gather, collapse, form the very first galaxies. Every galaxy, every cluster, every thread in the cosmic web traces back to a quantum fluctuation, magnified beyond imagination, that flickered into existence 1/10,000,000th of a trillionth of a second after the universe began. All the vast structures we see today, the flatness, the uniformity, the seeds of future galaxies, emerged from an event that lasted less time than it takes light to cross a single atom. The universe didn't acquire its fundamental features over billions of years. It happened in a single, unimaginably brief breath. But this breath left behind something peculiar. Space itself stretched to enormous scales, blistering with unimaginable heat, yet almost completely empty. No atoms, not even particles as we know them. So where did all the matter that makes up us and everything around us come from? The answer hides within the very mechanism that expanded the universe itself. At the heart of cosmic inflation lies a hypothetical scalar field called the inflaton. This isn't a particle, radiation, or matter as we usually understand it. It's a field permeating all of space, carrying one almost absurd property: anti-gravity. Instead of pulling matter together, the inflaton pushed space outward from within. Its energy forced the tiny seed of the universe to swell by a factor of 10 to the 50th power in just a fraction of a second. Put simply, it's like a spring compressed to the extreme. While it remains compressed, it drives everything around it with tremendous force. But no spring stays compressed forever. And this is where the most crucial part begins. Inflation didn't just stop, it exploded. The energy from the inflaton field didn't vanish into thin air. It shattered, unleashing a torrent of elementary particles. Quarks, electrons, neutrinos, photons. Everything that would later build matter surged into space in a single, instantaneous burst. Physicists call this process reheating. In other words, the spring released its tension, and all the energy stored inside transformed into matter. This is the true moment when matter was born. This event scale is hard to wrap your mind around. At the moment of the universe's reheating, temperatures soared to about 10 to the 27th power kelvins. To put that in perspective, the surface of the sun sits at a mere 5,800 kelvins. The sun's core burns at 15 million kelvins. The most powerful thermonuclear explosion humanity has ever created reached hundreds of millions. But here, 10 to the 27th. This isn't just hot. It's a temperature where the very idea of matter loses all meaning. At such extreme heat, atoms cannot hold together. Atomic nuclei fall apart. Even protons and neutrons break down into their building blocks. The universe was a seething, boiling broth of quarks and gluons, particles normally locked forever inside protons and neutrons. This was quark-gluon plasma, a state of matter unlike anything found anywhere else or at any other time, except during the first microseconds after the universe reheated. If by some miracle you could touch this environment, though touch hardly applies, since a finger, a carbon atom in that finger, and its electron clouds simply couldn't form, what you'd feel is closest to plunging into a thick, blazing liquid where everything crashes into everything else trillions of times each second. Physicists at the Large Hadron Collider try to recreate tiny droplets of this plasma by smashing lead nuclei at near light speed. Each droplet lives for just 1/quintillionth of a second. Yet, in that brief instant, they observe something remarkable. This plasma behaves exactly like a liquid, the most perfect liquid in the universe, almost without viscosity, almost without friction. Now this raises a truly unsettling question. We've described how the inflaton's energy transformed into particles. We've explained how those particles filled the blazing hot space. But where did the inflaton itself come from? Where did the very first spark come from that set this entire chain in motion? The answer lies deep within the foundations of quantum mechanics. According to Heisenberg's uncertainty principle, absolute emptiness doesn't exist. Even in a perfect vacuum, with no particles, no photons, fluctuations constantly occur. These are spontaneous bursts of energy, during which pairs of virtual particles appear out of nowhere. A particle and its antiparticle flash into existence, survive for a tiny fraction of a second, and then annihilate each other, returning the borrowed energy back to the vacuum. This isn't just a metaphor, it's a measurable physical phenomenon, confirmed in laboratory experiments. Most of these fluctuations collapse instantly. They appear, then vanish. Appear, then vanish again. Trillions of times every second. At every point in space, right now. Including in the air right in front of your face. But about 13.8 billion years ago, one of these fluctuations didn't collapse. Instead of disappearing, it became a seed. The tiny subatomic spot that cosmic inflation then expanded into the vast universe we observe today. Why did this particular fluctuation survive? We don't know. Maybe countless such attempts happened, and only one randomly proved stable enough. Or perhaps every surviving fluctuation spawns its own universe, and ours is just one among an infinite number. This isn't science fiction. It's a working hypothesis known as eternal inflation. And so far, we have no way to test it. One thing we know for sure. After reheating, the universe became a trillion-degree cauldron, packed to the brim with quarks, gluons, electrons, neutrinos, and photons. The inflaton's energy didn't vanish. It transformed into all of this. Every atom in every star, every molecule in every living cell, that's the legacy of the moment when the field discharged, flooding space with matter. But it wasn't just particles that emerged from that energy. Each particle came paired with its opposite, an antiparticle. Matter and antimatter, in exactly equal amounts, filled every cubic millimeter of the primordial soup. Equal. And then it happened. Every quark found its antiquark. Every electron met its positron. When a particle collided with its antiparticle, both vanished, turning into pure light. Two masses became two photons, completely, without residue, without a trace. This wasn't a disaster, it was arithmetic. If the energy creates exactly as much matter as antimatter, and the laws of physics demanded precisely that, then each particle is doomed to find its twin and perish alongside it. 1 billion pairs are born, 1 billion pairs annihilate, another billion, and another billion flashes. The universe should have consumed itself within fractions of a second and ended up empty. No atoms, no stars, just an endless ocean of light cooling into darkness. This isn't a pessimist's guess. It's a direct consequence of the standard model of particle physics. According to every equation we know, the cosmos right after the Big Bang had to be dead, filled with radiation, and nothing else. Here's the puzzle. I'm speaking these words right now. Sound waves push through air made of nitrogen and oxygen atoms. These atoms exist. They're made of something, protons and neutrons that logically shouldn't have survived the universe's first second. So, where did the symmetry go? The answer almost sounds like a rounding error. For every billion pairs of particle and antiparticle, there was one, just one, extra particle of normal matter, without a matching antiparticle, no partner to annihilate with. A billion antiparticles met their billion particles, flashed into light, and vanished. But this one particle stayed behind, like the last person left in an empty room after everyone else paired off and left. Let's try to turn this into a feeling. Imagine a stadium packed with 1 billion fans wearing red shirts, and another billion wearing blue. At the whistle, every red-shirted fan finds a blue-shirted partner, and they both leave the stadium. Within a minute, the arena is empty. Almost. There's one spot left, occupied by a single person in a red shirt. He just couldn't find a match. The entire visible universe, every galaxy, every star, every planet, every molecule inside every living cell descends from that one unmatched individual. The other 999,999,999 vanished. They turned into photons. They became the background. That background, by the way, still exists today. We call it the cosmic microwave background radiation. But we'll return to that later. Scientists observed a tiny imbalance, just one extra particle out of a billion. But the real puzzle was why? Why did nature favor matter, even slightly? What could have tipped the scales and broken perfect symmetry? In 1967, a man best known for something entirely different took on this challenge. Andrei Dmitrievich Sakharov, at the time one of the chief architects of the Soviet hydrogen bomb, a secretive physicist working in the closed city of Artemis 16, a man who, just a few years later, would become the country's leading dissident and a Nobel Peace Prize laureate. But in '67, he was still writing equations, not protest letters. It was then that he laid out 3 conditions the universe must meet to produce an excess of matter over antimatter. 3 mathematically precise requirements for the physics of the early universe. Without them, asymmetry simply couldn't exist. These are known as Sakharov's conditions: violation of baryon number, violation of charge symmetry, and departure from thermal equilibrium. It sounds dry, yet behind each of these points lies a concrete physical process, one without which not a single atom in your body could exist. Here's what truly unsettles scientists. We know the asymmetry existed. We see its effects all around us. We understand the conditions that could have sparked it, yet the exact mechanism that triggered it remains a mystery. No particle accelerator on Earth has managed to recreate the process that explains why, for every billion antiparticles, there was one extra matter particle. The standard model predicts an asymmetry far too weak, orders of magnitude smaller than what we observe. That means there's some physics out there we have yet to discover. But here lies the result of this undiscovered physics. All the hydrogen and helium that, after millions of years, will ignite the very first stars. Every heavy element those stars will one day cast out into space. Every atom of carbon in every organic molecule. All of this is a remnant, just 1/billionth of what once existed. A fragile film of matter surviving the greatest fire in history. And from this thin layer, the universe had to build everything. Fast. Because the window for the next step was already closing, and it came with a strict deadline. 180 seconds. That's all the time the universe needed to decide what it would be made of for the next 13.8 billion years. Not millions, not thousands. 3 minutes. About the time it takes to boil a soft-boiled egg. 1 second after the Big Bang, temperatures still soared into the billions of degrees. Protons and neutrons, the particles that survived annihilation, raced through the blazing hot mess at incredible speeds. At such extreme heat, any nucleus that formed from 2 or 3 particles shattered instantly. It was just too hot. Imagine trying to glue together a model airplane inside a roaring blast furnace. The glue evaporates faster than it can set. But the universe kept expanding and cooling. Somewhere between the first second and the third minute, the temperature dropped into a narrow window, around 1 billion degrees. Hot enough for protons and neutrons to overcome their electromagnetic repulsion and fuse on collision, yet cool enough for the newly formed nuclei to hold together instead of flying apart with the next impact. This window, a slim strip between too hot and too cold, marked the critical deadline, the primary nucleosynthesis. The first and only moment when the entire universe acted like one massive thermonuclear reactor, from edge to edge. A proton captured a neutron, forming deuterium, or heavy hydrogen. When two deuterium nuclei collided, helium-3 was born. Add another neutron, and you get helium-4, a stable nucleus made of 2 protons and 2 neutrons. The chain reaction raced forward, fast, hungry, relentless. The byproducts? Traces of lithium and a bit of leftover deuterium that didn't get a chance to react. Here lies the crucial question. Why did the chain stop at helium? Why didn't it push further to carbon, oxygen, or iron? The answer seems deceptively simple. The universe cooled down. By the end of the third minute, expansion had dropped both temperature and density so low that nuclear reactions became impossible. Particles sped apart faster than they could collide. The reactor shut down, not because it ran out of fuel, there was plenty of it, but because the reactor's walls, so to speak, had drifted millions of miles apart and the pressure fell below the threshold. In other words, space had grown too vast and too cold to fuse anything heavier than helium. The outcome of those 180 seconds sealed the deal. 75% of ordinary matter stayed as hydrogen, single protons that never found a partner. 25% transformed into helium. Lithium and deuterium made up just a fraction of a percent, a statistical blip compared to the two main players. This recipe locked in. No process in the universe could change it. Until hundreds of millions of years later, when the first stars ignited, firing up their own thermonuclear furnaces. 3 minutes set the chemical makeup of the cosmos for billions of years to come. But this isn't just a neat statement, it's a testable prediction. And here's where things get really fascinating. In the mid-20th century, physicists developed the hot Big Bang model and calculated specific numbers: how much helium, how much deuterium, how much lithium should have formed. These numbers didn't come from fitting data, they emerged directly from the equations. Then, astronomers began measuring helium levels in the oldest, chemically untouched regions of space, gas clouds that had never been part of stars, never processed or enriched with heavy elements. Spectrometers revealed helium made up about 24 to 25% of these clouds, exactly the amount the theory predicted. Measurements of deuterium in intergalactic gas matched the calculations too. Every independent measurement, different telescopes, different wavelengths, different patches of sky, pointed to the same numbers. When a prediction and observation match this precisely, it's no coincidence. It's a signature, a proof that we truly grasp the physics of those first moments. Yet the universe that forged its first stable atomic nuclei was still blind. A searing plasma of nuclei, electrons, and photons filled the cosmos, dense and opaque, like a thick fog that allowed no light to pass. Photons bounced endlessly among charged particles, trapped with nowhere to escape. This fog would linger for 380,000 years, until the temperature dropped enough to change everything. 380,000 years. That's how long this blindness lasted. Photons were born, traveled, collided with free electrons, changed direction, and set off again, only to collide once more. In this plasma, a particle of light traveled only a tiny distance on average. Imagine a flashlight in a thick, milky fog. The beam exists, but visibility drops to zero. Light was there, and energy overflowed, yet there was nothing and no one to see it. The universe gleamed from within, and yet remained utterly opaque. Simply put, every photon was trapped. Not behind bars or walls, but stuck in a crowd. Charged particles packed so tightly that light physically couldn't travel any meaningful distance without bumping into another electron. Let's pause here and really grasp the scale. 380,000 years. That's not just a random number. All of human written history spans roughly 5,000 years. Multiply that by 76. That's how long the universe spent as a blazing, opaque fog where not a single ray of light could reach its destination. After 1,000 years, the plasma cools down slightly. 10,000 years in, space expands and temperatures drop even more. At 100,000 years, electrons still race too fast, too hot, to settle near atomic nuclei. 200,000 years later, they slow down a bit, but it's still not enough. 300,000 years? Almost there. Almost. And finally, around 380,000 years, the temperature falls to about 3,000 degrees Kelvin. Still hotter than the surface of some stars, but for that early cosmos, it marked a turning point. At this temperature, electrons finally slowed down enough for the nuclei of hydrogen and helium to capture them. An electron approaches a proton, and it sticks. It doesn't bounce off or fly away. For the first time in the history of the universe, a neutral atom forms. Physicists call this process recombination, although the name is misleading since electrons and nuclei were coming together for the very first time, not again, but the term stuck. Here's what happened next. Neutral atoms are transparent to light. Photons no longer have charged targets to bounce off. The fog lifted. Not gradually, not over millions of years, but on cosmic timescales, almost instantly. The universe, which had been an impenetrable wall for 380,000 years, suddenly became clear, and light began to travel. Here's the fascinating part. That light never disappeared. It didn't fade away, scatter, or get absorbed. The photons released at the moment of recombination are still traveling through the expanding cosmos. Right now. They fill every corner of the universe, every single cubic centimeter. This is the cosmic microwave background radiation, the oldest light we can possibly see. A snapshot of the universe when it was just 380,000 years old, a tiny infant by cosmic standards. But who actually discovered it? This is where the story takes an unexpected turn. Theorists had predicted this radiation back in the late 1940s. In 1948, Ralph Alpher and Robert Herman calculated that the leftover glow from the hot early universe should still be around today, cooled down to just a few degrees above absolute zero. Their calculation was published. People read it, then promptly forgot about it. For 15 years, the work gathered dust. No one tried to detect this radiation. Then, in 1964, in New Jersey, two radio engineers, Arno Penzias and Robert Wilson, were calibrating a horn antenna built for satellite communication. The antenna picked up a strange background noise. It was steady, faint, and the same in every direction. Penzias and Wilson checked everything: interference from the city, electronic crosstalk, flaws in the antenna itself. They even found pigeons nesting inside the horn. They cleaned out the droppings thoroughly by hand. Yet the noise persisted. It didn't depend on the time of day, the antenna's direction, or the season. It came from everywhere. Two engineers, not cosmologists, not theoretical physicists, held a signal 13 billion years old, and they had no idea what it was. The breakthrough came when their colleagues at Princeton, just 37 miles away, heard about the mysterious noise and instantly recognized it. This was the very same light, cooled down and stretched by the expansion of space from visible wavelengths into microwaves. But the exact signal predicted 16 years earlier and dismissed at the time. Over billions of years, this radiation has cooled to just 2.7 degrees above absolute zero. It once blazed at 3,000 kelvins, a fiery orange glow. Now it's colder than anywhere on Earth's surface. colder than the darkest night on Pluto. Yet it still exists. We can measure it. Its temperature matches the predictions of the hot Big Bang model with such precision that no alternative explanation holds up. When an old analog TV loses signal between the antenna and the set, about 1% of the static you see is this cosmic microwave background radiation. That flicker on the screen hides the echo of the universe's birth. And here's the key. This light marks a boundary. We can't look beyond it. Not because there's nothing there, but because before recombination, the universe was opaque. Any information carried by photons got wiped out by endless collisions. The cosmic microwave background is a wall. Our eyes, telescopes, and antennas will never see beyond it. It's the earliest and most distant snapshot light could ever capture. But once that light was free, darkness took hold of the universe. Neutral hydrogen and helium atoms filled the space, but they didn't shine on their own. Stars hadn't formed yet. Nothing burned, nothing radiated. Ahead lay hundreds of millions of years of silence, gravity slowly, patiently drawing scattered gas into the first clumps. Not stars, not even star embryos, just slightly denser pockets in the vast emptiness, waiting for their moment to shine. Darkness lasted longer than anything we've ever experienced, longer than the entire history of life on Earth, longer than the reign of dinosaurs, mammals, and civilizations combined, multiplied by 10. After the relic radiation burst free and the universe became transparent, a new era began, what cosmologists call the Dark Ages. No stars, no sources of light, just an expanding space filled with neutral hydrogen and helium, a gas slowly cooling in absolute impenetrable blackness. Try to grasp the scale. 1 million years pass after recombination. The gas cools slightly, space expands a bit, yet nothing changes. 10 million years later, the temperature drops to just a few dozen kelvins. Hydrogen atoms drift through the void, never touching. 50 million years in, if an observer existed, they would see absolutely nothing. No points of light, no glimmers. 100 million years, still the same darkness, the same cold, the same gas. 200 million years, 300. On Earth, continents would break apart and come back together in that time. But here, nothing visible happens. The universe remains silent. Yet this silence is deceptive. Because in the darkness, a force worked that didn't need light. Gravity didn't rush. It had nowhere to hurry to. In the first seconds after the Big Bang, tiny quantum fluctuations, density variations smaller than an atom, stretched out across the cosmos by inflation. Now, hundreds of millions of years later, these faint clumps began gathering matter around themselves. Where density was just a fraction of a percent above average, gas pulled in a little more strongly. A little stronger pull meant a little more mass. More mass meant even stronger attraction. A feedback loop unfolding with a patience no geological process could ever match. And this is where things get truly strange. Ordinary gases, hydrogen and helium, wouldn't have had enough time to clump together into dense structures on their own. Calculations show that if the universe contained only visible matter, gravity alone wouldn't have been strong enough. Clouds of gas would have expanded faster than they could contract. But gravity had help from an invisible framework. Dark matter, the substance that neither emits, absorbs, nor reflects light, had already carved out gravitational wells long before ordinary matter started to fall into them. Simply put, dark matter dug the wells, and hydrogen and helium slowly flowed into them, like rainwater filling ravines. These invisible wells weren't scattered randomly. They formed structures, long strands and knots, like a three-dimensional web stretching across the entire universe. Ordinary gas followed this framework obediently, condensing at the knots, stretching along the threads. But stars were still far away. The gas had to grow dense and hot enough at the very center of the clump to spark the one process that could turn darkness into light: nuclear fusion. Somewhere between 100 and 200 million years after recombination, it's hard to be more precise, The pressure and temperature in the core of one gas cloud reached a critical point. Hydrogen nuclei began colliding with such force that electromagnetic repulsion no longer held them apart. They fused. Energy was released. The first photon of a new kind, not relic radiation, not leftover light, but born from nuclear fusion, escaped from the heart of the gas cloud. The first star ignited. Astrophysicists call these objects population 3 stars. None of them have survived to the present day. We've never observed a single one directly. But calculations and computer models paint their portrait with striking clarity. These stars were nothing like our Sun. They were monsters. Their mass measured in the hundreds of times that of the Sun. Some models suggest 300, 400, even 1,000 times the Sun's mass. Their surface temperatures soared to tens of thousands of kelvins. Their brightness outshone the Sun by millions of times. And yet, they consisted solely of hydrogen and helium. No carbon, no oxygen, no iron. Just 2 elements born in the first moments after the Big Bang. This made them fundamentally different in structure. Without heavy elements, the gas cooled more slowly, and the clouds fragmented less. The result? Not a cluster of small stars, but isolated giants, colossal and singular. But size comes with a price. The bigger the star, the faster it burns through its fuel. Our Sun will last about 10 billion years. A star 300 times heavier than our Sun burns out in just 2 to 3 million years. On a cosmic scale, that's a flash. A brief, blinding burst of light against hundreds of millions of years of darkness. Where did all that energy go? What happens when the fuel runs out? The first stars were nothing like our Sun, not just in life, but in death as well. They ended with explosive, catastrophic blasts, scattering their material across vast stretches of space. And it was in these explosions that the universe first gained something it had never had before. New elements scattered across space. Carbon, oxygen, silicon, iron, all the building blocks that hadn't existed before now drifted through the expanding void. You might think the story is simple from here. Gas cools, contracts, stars ignite, and planets form around them. But something doesn't add up. Take ordinary matter. Protons, neutrons, electrons, all these freshly forged atoms, and run a computer simulation, letting it run for 13.8 billion years. What happens? No galaxies. Not enough time. Gravity from normal matter just isn't strong enough to pull scattered gas into structures even remotely like the Milky Way. The model spits out a uniform fog. No spirals, no elliptical clusters, nothing. This is where the mystery begins, the puzzle astronomers have wrestled with for decades. If regular matter isn't enough, then what exactly pulled galaxies together? The logical step was to search with telescopes. Look deeper, farther, across different wavelengths. Optical telescopes didn't reveal the answer. Infrared observations didn't help either. Radio telescopes, X-ray observatories, gamma-ray detectors, every new tool confirmed the same unsettling fact. There was a shocking shortage of visible matter. But the breakthrough didn't come from those building ever more powerful telescopes. It came from those measuring speed. In the 1970s, Vera Rubin was doing what seemed routine, measuring how fast stars move at the edges of galaxies. According to Newton's laws, the farther a star is from the center, the slower it should orbit. Just like Neptune moves slower around the Sun compared to Mercury. But stars at the edges of galaxies spun too fast. Not just a little faster, radically faster. It was as if the galaxy hit a mass no one could see. A mass that neither shines, nor absorbs light, nor emits anything in any part of the spectrum. And yet, it pulls. It exerts gravity. 85% of all matter in the universe isn't made of atoms, not protons or neutrons. It's something that doesn't interact with light at all. Dark matter. You can't see it, touch it, or detect it with any electromagnetic sensor. Yet its gravity built the invisible framework that shaped every galaxy, including our own. Without this framework, ordinary matter wouldn't have had time to clump together in the lifespan of the universe. Simply put, everything we see in the night sky hangs on a skeleton made of something we can't observe. And here's where it gets even stranger. This skeleton isn't just a shapeless mass. It has a structure, a design. Imagine stepping far enough away from the universe that entire galaxies shrink to mere points and clusters of galaxies blur into faint smudges. The view wouldn't be random or evenly scattered. You would see a vast cosmic web, a sprawling three-dimensional network of threads called filaments stretching across hundreds of millions of light years. At the intersections of this web, where matter densifies the most, lie galaxy clusters, hundreds, even thousands of galaxies pulled tightly together by gravity into a single knot. Our own Milky Way belongs to the Laniakea supercluster, a colossal structure about 520 million light-years across, holding roughly 100,000 galaxies. That's just one node. One. And yet, this cosmic web extends far beyond, spanning billions of light-years in every direction. Imagine looking at a wet sponge cut in half. Thin strands of material form a framework, while the spaces in between are filled with air. But the scale we're talking about here is entirely different. Each strand is a chain made up of thousands of galaxies. Each empty space is an expanse where almost nothing exists. These voids deserve their own spotlight. They are enormous bubbles of space, hundreds of millions of light-years across, where the density of matter falls to a fraction of the universe's average. This isn't just a place with fewer stars, it's nearly complete emptiness. One of the largest is the Boötes Void. It measures 330 million light-years wide. Light traveling from one edge of this void, starting when dinosaurs were nowhere on Earth, still hasn't reached the other side. Inside, only a few dozen galaxies reside. By comparison, an average volume this size should contain roughly 2,000. It's silence on a scale that challenges our very understanding. Voids are more than just empty spaces. They expand. Dark energy, the mysterious force driving the universe's accelerating expansion, acts strongest inside them. That's because voids contain the least matter to push back against it. By studying how fast these voids grow, cosmologists hope to unlock the secrets of dark energy, another invisible force we understand even less than dark matter. Here's what blows your mind if you stop and really think about it. This entire cosmic web, filaments stretching billions of light-years, clusters made up of thousands of galaxies, voids spanning 300 million light-years, all of it traces back directly to events in the universe's first fractions of a second. Tiny quantum fluctuations, microscopic patches of uneven density that appeared when the universe was smaller than an atom. Then, inflation stretched these ripples to cosmic proportions. Dark matter gathered in these slightly denser regions, pulling in ordinary matter. Filaments formed where the original density was just a bit higher. The voids appeared where it was slightly lower. The difference in density? 1 part in 100,000. An almost imperceptible ripple, yet it became the skeleton of everything. Here's a strange fact. Everything we see, stars, galaxies, clusters, the entire large-scale structure of the cosmos, makes up only about 15% of its story. That's just the surface, a thin, glowing film on the edge of something vast and invisible. 85% of the matter shaping the universe has never emitted a single photon. We live inside a framework built from substance that, for us, quite literally doesn't exist, except for one thing: it pulls. And that alone has been enough. Yet even within this unseen skeleton, things happen that defy our calculations. Modern telescopes peering back into the first billion years of the universe reveal objects that, according to every model, shouldn't have grown so quickly. What if black holes didn't grow, but were born huge? It sounds absurd. The standard model says this: a massive star dies first. What's left is a compact remnant, a black hole weighing a few dozen times the mass of our sun. Then it sucks in gas, dust, even other stars. It gains weight. Slowly, step by step, century after century, billion after billion of years. It's a straightforward process. Yet it has a physical limit, the so-called Eddington limit, where radiation pressure pushes back against falling matter. A black hole can't eat faster than a certain speed. It's like trying to drink water from a fire hose. Your throat just can't handle it. And that's where the real problem begins. On December 25, 2021, the James Webb Space Telescope launched from the Kourou spaceport. Its infrared mirrors reached farther than any instrument before, peering into the universe's first 500 to 700 million years after the Big Bang. What did it find? Supermassive black holes. Not tiny seeds, not modest leftovers of the earliest stars. Monsters weighing billions of times the mass of our sun. Billions. At a time when the universe was less than 700 million years old, about 5% of its current age. Imagine discovering a century-old oak tree in a garden that was planted just yesterday morning. According to every calculation, there simply hasn't been enough time for such growth. Even if a black hole had been feeding at its maximum rate since the very first second of its life, it still wouldn't have enough time to reach billions of solar masses. Physically impossible. So either we've been calculating their growth rate wrong, or these black holes didn't start out with just a few dozen times the mass of our sun. They began with something much larger. Here, one of the most elegant hypotheses in recent years comes into play: direct collapse. The idea goes like this. In the early universe, enormous clouds of primordial gas, mostly hydrogen and helium, existed, each weighing hundreds of thousands of times more than our sun. Normally, such a cloud would fragment. It cools down, breaks into pieces, and each piece births a star. But if a powerful source of ultraviolet radiation was nearby, like a neighboring young galaxy, it would destroy hydrogen molecules, preventing the gas from cooling effectively. The cloud couldn't fragment. Instead, it collapsed all at once. Not into a star, straight into a black hole weighing 100,000 times the mass of the sun, skipping the star stage entirely. These seed black holes, if they truly existed, got a massive head start. They didn't have to build up mass from scratch. They began heavy and became the hubs around which the first galaxies took shape. More precisely, they became that way according to one hypothesis. But confirming this with observations remains extremely difficult. But we can still see something. Quasars are the active cores of galaxies, where supermassive black holes ravenously consume surrounding matter. As gas falls into a black hole, it accelerates to staggering speeds, heats up to millions of degrees, and starts to glow. Brighter than the entire galaxy around it. Brighter than 1 trillion stars. Quasars rank among the brightest objects in the universe. That's why we can spot them from 13 billion light-years away. They act like beacons, illuminating the early universe from within. As quasar light travels toward us, it passes through clouds of intergalactic gas, carrying clues about the composition, temperature, and density of the space it crossed. Without quasars, we wouldn't even know these ancient black holes existed. They played a crucial role in reionization, the process where ultraviolet radiation from the first bright sources ionized the neutral hydrogen filling the universe after the era known as recombination. Quasars literally helped make the cosmos transparent. Here's the crucial point. Finding these black holes that are too massive, too early in the universe's history, that's not a failure of cosmology. It's how science actually works. The theory makes a prediction. Observations prove it wrong. Scientists don't hide the data. They search for new explanations. Direct collapse is one possibility. Mergers of primordial black holes are another. Super Eddington accretion under special conditions is a third. None of these have been confirmed yet. We still don't know exactly how the universe built its first giants, but every new image from the James Webb Space Telescope narrows down the possibilities. And at the same time, it opens up new questions, because every answer leads to 3 more. Yet this isn't the only mystery space has thrown at us in recent decades. The most shocking discovery wasn't about the universe's past. It concerned its future. 1998. 2 independent teams of astrophysicists, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, are studying distant Type 1a supernovae. These explosions of dying white dwarfs are powerful because their peak brightness is almost the same. They serve as standard candles. By knowing a supernova's true brightness and measuring how dim it appears from Earth, scientists can pinpoint its distance with precision. Then, by comparing that distance to its redshift, they can determine how fast the universe was expanding at different times. Both teams expected the same result. The expansion should be slowing down. Gravity pulls matter back, breaking the galaxy's flight apart. It seems so obvious that the only question was how quickly the expansion was decelerating. But the data told a different story. Distant supernovae appeared dimmer than the model predicted, with a slowing expansion. Actually, much dimmer. They were farther away than they should have been. And that meant one thing: the universe's expansion isn't slowing down, it's speeding up. Galaxies are racing away from each other faster with every billion years. Perlmutter later recalled that the team's first reaction wasn't excitement, it was suspicion that something had gone wrong. For months, they double-checked calibrations, hunted for systematic errors, and changed their analysis methods. Yet the results never wavered. When a second group, working completely independently, came up with the same numbers, it became clear there was no mistake. In 2011, all three received the Nobel Prize in Physics. And here lies the greatest mystery. What exactly is driving the universe's acceleration? Gravity, the only force at work on cosmic scales, pulls. It slows things down, draws them together, squeezes. For the expansion of the universe to speed up, something must push back. Something that drives space apart from within. Physicists call this mysterious force dark energy. Not because it's literally dark, but because we have no clue what it actually is. The only thing we know for sure is that dark energy makes up about 70% of the universe's total energy budget. 70%. Imagine living in an apartment where someone occupies 3 out of 4 rooms, pays most of the utility bills, but you've never seen or heard them, and you can't even prove they exist. Yet somehow, they control the temperature inside the whole building. Regular matter, the stuff that makes up stars, planets, gas clouds, and us, accounts for about 5% of the universe. Dark matter, which neither emits nor absorbs light but pulls through gravity, adds roughly 25%. The remaining 70% is something else entirely. It behaves like anti-gravity, and modern physics still can't explain what it is. This isn't just another unsolved problem on a long list. It's a chasm at the very foundation. When theoretical physicists try to calculate the energy of the quantum vacuum, that is, the energy of empty space predicted by quantum mechanics, they end up with a number that differs from the observed dark energy by a factor of 10 to the 120th power. This is the biggest gap between theory and experiment in the entire history of physics. Not twice as big, not 1,000 times, but one followed by 120 zeros. Nobel Prize winner Steven Weinberg called the cosmological constant, the mathematical counterpart of dark energy, a thorn in the side of theoretical physics. And even 25 years after the discovery of the universe's accelerated expansion, that thorn remains. We have no idea what dark energy really is. We don't know why it has exactly this strength. We don't know if it has changed over time or stayed constant. Yet, one of the simplest hypotheses takes us back to the very beginning, to the energy of the vacuum itself. The energy of emptiness. That same nothing from which the universe might have been born. If that's true, then emptiness didn't just give rise to everything at the moment of the Big Bang. It's still at work right now, everywhere in space, pushing galaxies apart. The initial condition never disappeared. It was just waiting for matter to spread out enough to take over again. Here's what truly unsettles scientists. With every passing billion years, matter becomes more and more scarce in any given volume. Meanwhile, dark energy, a property of space itself, doesn't dilute. The more space there is, the more dark energy there is. That means dark energy's influence will only grow stronger. Stars that haven't yet ignited from the intergalactic gas might never get the chance, because that gas will become too thin. And galaxies we see now on the horizon will eventually cross it and vanish forever. The observable universe's horizon will shrink, not because the universe is getting smaller, but because it expands so rapidly that light can't keep up. Iron flows through our blood. Calcium forms the bones. Phosphorus builds the molecules that store our genetic code. None of these elements existed in the first moments after the Big Bang. Hydrogen, helium, and a tiny trace of lithium made up the entire initial mix. The periodic table had only 3 rows. The rest was an empty promise. To fulfill that promise, the universe had to create furnaces. A star is basically a nuclear fusion reactor powered by gravitational compression. Inside the core of an ordinary star like our Sun, hydrogen fuses into helium at around 15 million degrees. But when the hydrogen fuel runs out, the core contracts even more. Temperatures soar, and a new cycle begins. Helium turns into carbon. Carbon transforms into oxygen. Oxygen becomes neon, magnesium, then silicon. Each new stage of burning demands even more extreme conditions. It's like trying to light a fire with heavier and heavier logs. Each one needs the heat from the last. Finally, deep at the center, where temperatures reach billions of degrees, silicon fuses into iron. Iron marks a dead end. Beyond this point, nuclear fusion stops producing energy. It starts consuming it instead. The core loses its support. In a fraction of a second, the star that resisted its own gravity for millions of years finally gives in. Its outer layers collapse inward, slam against the ultra-dense core, and then explode outward at tens of thousands of kilometers per second. A supernova. One single exploding star outshines an entire galaxy for weeks. And in that explosion, in that monstrous shockwave, carbon, oxygen, silicon, iron, everything the star forged during its lifetime gets flung into interstellar space. Simply put, stars don't just burn, they work. And when they die, they share the fruits of their labor. Here's the puzzle. Supernovae explain how elements up to iron form. But what about gold, platinum, uranium? Creating these elements requires conditions that even a supernova can't provide. This was a mystery that nuclear physicists couldn't solve for decades. The answer didn't come from a lab. It came from a gravitational wave observatory. In 2017, detectors recorded the collision of 2 neutron stars in a galaxy 130 million light-years away. Each neutron star is essentially an atomic nucleus the size of a city, about 12 to 15 kilometers across, but heavier than our Sun. When 2 of these objects slam into each other, the temperature and pressure in the impact zone exceed anything even the most massive supernova can generate. It's in this fiery, millisecond-long collision that the heaviest elements on the periodic table emerge: gold, platinum, uranium. Calculations show that a single merger can fling into space an amount of gold equal to several moons. That wedding ring on your finger? It's literally a fragment from 2 dead stars that tore each other apart billions of years ago. Meanwhile, the first stars were doing more than just creating elements. After the Big Bang, the universe entered a long stretch of darkness, hundreds of millions of years without a single light source. Space filled with neutral hydrogen, a thick fog so opaque that not a single photon could break through. Then, the first stars and the earliest quasars, supermassive black holes devouring matter with fierce brightness, began emitting powerful ultraviolet light. This radiation tore hydrogen atoms apart, splitting them into protons and electrons. It reionized the gas. This process is called reionization, the universe's second major phase transition. The first happened about 380,000 years after the Big Bang, when plasma cooled and turned into neutral gas. Now, after several hundred million years, that gas became plasma again, but this time it was thin and transparent. Space cleared out. Light could finally travel vast distances without crashing into walls of atoms. The universe we see today, clear and glowing with the distant light of billions of galaxies, became possible at that moment, roughly 1 billion years after it all began. In 1957, 4 physicists, Margaret Burbridge, Geoffrey Burbridge, William Fowler, and Fred Hoyle, published a paper still known simply by their initials. For the first time, they systematically showed that every element heavier than helium forms inside stars. But 4 years before that paper, Hoyle made an even more astonishing prediction. He proposed that the carbon-12 nucleus must have a specific energy level. Without it, stars couldn't produce enough carbon, and without carbon, there would be no oxygen, no life. Nuclear physicists greeted this claim with skepticism. Then they tested it. The energy level turned out to be exactly where Hoyle said it would be. Armed only with logic and a deep understanding of stellar processes, this astrophysicist predicted a property of the atomic nucleus that nuclear physicists had completely missed. 14 billion years ago, there was nothing but energy and the simplest particles. Then hydrogen appeared. Hydrogen gathered into stars. Those stars forged it into carbon, oxygen, and iron. When dead stars collided, they created gold. Clouds of enriched gas collapsed into new stars, surrounded by rocky planets infused with this chemistry. On one of those planets, carbon, hydrogen, oxygen, and nitrogen combined into a molecule able to replicate itself. After 4 billion years of evolution, that molecule became a being that looks up at the stars and asks where it came from. The answer, from there, from those very stars. But this story has an expiration date. Stars won't burn forever, and the space between galaxies expands with every passing second. In 100 trillion years, the last star in the universe will burn through the final bits of hydrogen and go dark. It won't explode or collapse, it will simply stop shining. Like a light bulb with a burnt-out filament. Only there won't be anyone left to replace it. If dark energy keeps dominating, and all current evidence points that way, the fate of the cosmos is sealed. The accelerating expansion will stretch the space between galaxy clusters faster than light can cross it. The most distant galaxies will vanish first, then the closer ones will follow. One by one, they will slip beyond our cosmic horizon and disappear forever. Not because they're destroyed, but because the space between us and them is expanding faster than light can travel. The stars still burning will slowly run out of fuel. No new stars will form. Gas clouds will thin out too much to collapse. The universe's temperature will drop, edging closer and closer to absolute zero, minus 273 degrees and 1500ths Celsius. This is the heat death scenario, the Great Freeze. No sound, no light, no warmth. Just an expanding void, barely above absolute zero in temperature, and sparse, unimaginably distant particles with nothing to interact with. But here's what gets truly eerie. Imagine that, trillions of years from now, a civilization rises in one of the surviving galaxies, perhaps born from the merger of the Milky Way and Andromeda. Intelligent beings build telescopes. They point them to the sky. What do they see? Nothing. Complete, utter darkness beyond their own galaxy. No signs of other star systems. No distant quasars. No traces of the cosmic background radiation. By then, it will have stretched into wavelengths too long for any instrument to detect. These astronomers will be brilliant. Maybe even smarter than us. They will build theories, run calculations, and map their galaxy down to individual stars. Yet, they will reach one clear conclusion. Their galaxy is the entire universe. A lonely island of matter, adrift in infinite emptiness. No Big Bang, no expansion, no 14 billion year history. All the evidence will have vanished, erased by the very expansion that once created it. Where did all the information go? It's not destroyed. It's simply beyond the horizon, forever out of reach, like a letter sent to an address that no longer exists. And here comes a chilling thought. We live in a narrow window of cosmic history. Right now, in this very era, we can still catch the afterglow of the Big Bang with an antenna. We can still measure the redshift of distant galaxies. The fingerprints of primordial nucleosynthesis remain visible in the ratio of hydrogen to helium. All the clues are still there. But this won't last. The universe slowly hides its own past, stretching, cooling, and diluting it until nothing readable remains. We have landed at the only moment when the universe still remembers how it was born, and we happen to be curious enough to ask. It's a strange coincidence. 1,000,000 years after the Big Bang, too early. No stars, no planets, nothing solid to stand on. 100 trillion years from now, too late. Every trace erased. But right now, 13,800,000,000 years later, both an observer and something to observe exist. The window is open, but it's closing. And here begins the question that haunts us. If the end result is cold emptiness, and the starting point was empty too, just extremely hot, then everything we know, stars, galaxies, life, consciousness, is a fleeting ripple between two forms of nothingness, a brief flash of complexity in the midst of eternal simplicity. Is it chance? Or does something behind this flash make it not just possible, but inevitable? Maybe the parameters of this universe aren't the only way it could be. Maybe there could be infinitely many. The answer is simpler than it seems, and that's exactly why it feels so unsettling. There's a hypothesis that Stephen Hawking, among others, supported. It goes like this. The total energy of the universe is zero. All matter, all radiation, every photon, every hydrogen atom, every star, that's positive energy. But gravity, which pulls everything together, carries negative energy. When you add these two up for the entire observable universe, they balance out to zero. Or at least, calculations show they come extremely close, perhaps exactly zero. In other words, the universe owes nothing to nature. It didn't borrow energy from any outside source. It didn't break a single conservation law. Because in the end, its balance sheet is empty. To get this right, you need a clear mental image. Start with zero, just a plain zero. Now split it into +1 and -1. The sum doesn't change, it's still zero. But suddenly, you have two things that weren't there a moment ago. +1, that's matter, stars, galaxies, you. -1, that's gravity, holding everything together and bending space itself. In this model, the birth of the universe isn't an explosion from nothing. It's zero splitting into two halves that perfectly balance each other. Not a law broken, a consequence of that law. Here's a principle to remember well beyond physics. When something looks like a gift from nowhere, check if zero has split into two debts with opposite signs. That's usually how it works. But let's say we accept this idea. Suppose the universe really could have popped into existence without any external push, without breaking any fundamental laws. That leads to an even more unsettling question. Why did it turn out exactly like this? Fundamental physical constants, the strength of gravity, the charge of the electron, the mass of the proton, the force of the strong nuclear interaction, all fall within a stunningly narrow range. This is the precise range where complex structures become possible. Atoms, molecules, stars, life. Change the strength of the strong interaction by just a fraction of a percent, and protons would fail to bind into nuclei. Stars wouldn't ignite. Carbon wouldn't form. We wouldn't exist. This is known as the fine-tuning of the universe, and it stands as one of modern physics' most troubling mysteries. Not because we lack answers, but because the two main answers are equally dizzying. The first answer is a logical one. It's called the anthropic principle. Its core idea sounds deceptively simple. We observe this kind of universe because, in any other, we wouldn't exist. There'd be no one around to ask the question. It's like being surprised you were born on a planet with oxygen. Well, of course. You wouldn't be here to wonder if there was no oxygen. It sounds like a truism, almost like a dismissal. But, strictly speaking, it holds up. Experts still debate whether this counts as a real explanation or just a restatement of the question. No clear consensus has emerged. The second answer is physical, and it's far more vast. The multiverse hypothesis suggests that our universe is just one bubble among countless others, floating in an ever-expanding cosmos. Each bubble has its own constants, its own physics, its own set of rules. In most of them, nothing interesting happens. Protons break down, or never form at all. Sometimes gravity is so strong, everything collapses back in milliseconds. But in one of these endless bubbles, in hours, the conditions happened to fall within just the right narrow range. Carbon emerged, water appeared, and someone capable of looking around and asking, "Why does it feel so right here?" The theory of eternal chaotic inflation, developed by André Linde, provides a solid mathematical foundation for this idea. But, and here we have to be honest, we don't know if the multiverse actually exists. We don't know if we can ever test it. It might remain forever beyond the horizon of what we can observe. Or maybe the next generation of cosmological observations will uncover indirect traces, imprints of our bubble colliding with a neighbor in the cosmic microwave background. For now, it's just a hypothesis. But it's a hypothesis that physics can express in the language of equations, and that takes it beyond philosophy. And here we have arrived at the question we started with. Why is there something rather than nothing? Physics offers a paradox that doesn't settle easily in the mind. Something emerged from nothing, because in the end, it still sums to zero. The universe is zero, broken down into parts. Matter and gravity are two numbers with opposite signs that, when combined, recreate the empty space from which everything began. But it isn't truly empty. What we call nothing isn't silence or darkness. It's a space brimming with hidden energy, governed by laws that make the birth of worlds less a miracle and more a matter of statistics. Absolute emptiness doesn't exist. The quantum vacuum isn't the absence of everything, it's the potential of everything, ready at any moment to split its zero into positive and negative, and start over. We don't know if our universe is the only one. We don't know if the appearance of an observer is inevitable. We don't know why the laws of physics exist at all. And that might be the deepest question science has ever touched, but still can't answer. But here's what we do know for sure. 13,800 billion years ago, zero split apart. Matter and gravity pulled away from each other. From that split, stars were born. Stars that cooked up carbon. Carbon gathered into planets. And on one of those planets, carbon learned to ask questions. Right now, in this narrow window of time when the cosmic microwave background still shines, when redshift remains measurable, when the clues are still intact, that carbon looks up at the night sky and tries to figure out where it came from. The answer turned out to be strange. It came from nothing. And this nothing is the most complete thing in the entire universe.